a specific inhibitor of an enzyme. So acetylcholinesterase, which happens to be the enzyme we're going to study with the insecticide, sarin urate gas can bind to an R group of one of the amino acids in the active site. So this is a case where it actually binds covalently, and it will inhibit that enzyme. And this enzyme is important for proper functioning of the neurons. That's why it's a nerve gas. So it will stop your neurons from working properly and it can kill you. Now, most of you are too young or were born after this incident in 1995, where a specific cult in Japan decided to attack the Tokyo subway using sarin nerve gas. And it killed a few people, sickened thousands of people. However, that wasn't their first choice. So a few of you who might be old enough to remember what happened in 1995, does anybody remember what their first choice was, which was a huge deal?
Syria.
Oh, it's being used in Syria now. I'm talking about Onshirikyo and what they tried to do in 1995 before they switched to a sarin urate gas, because they weren't quite able to do the other thing they wanted to do. First choice wasn't sarin urate gas. It was Ebola. They weren't able to weaponize Ebola, which is very lucky for us. So they used sarin urate gas. Now, you may not be aware of this, but antibiotics also are enzyme inhibitors. So penicillin happens to be an inhibitor of an enzyme that bacteria use to make their cell walls. So if they don't have an active form of that enzyme because of this inhibitor present, then they can't replicate. And so that allows you to fight the infection, this infection. So all of the penicillin family antibiotics, penicillin, amoxicillin, they all work the same way. They block the enzymes that bacteria use to make their cell walls. All right, just as an aside, you may not know this, but in the 60s, the US government decided to find out how quickly something like sarin urate gas or some other chemical or biological weapon could spread through the New York subway. So they actually used a non-virulent bacteria, and they introduced it in one subway station. And then they checked to see how long it took for it to get to all the other subway stations in the city. How long do you think it took? That would be too optimistic. It took less than 24 hours. So less than 24 hours, the entire subway system was infected by that bacteria. Now they used a non-virulent one here in the 60s, 65, 66, if I remember correctly. But before that, in the 50s, they had done a similar study, well, not exactly similar study. They had done a different study off the coast of California, off San Francisco, to find out how bacteria used as a biological weapon could be spread along California given the wind patterns off the coast. So they introduced this, in that case, a virulent form of a bacterium, and then they tracked to see what happened. And actually several people got sick, and I think a couple of people died. And so that was the experiment in the 50s, and then when they did the one in New York in the 60s, they switched to a non-virulent form so that they wouldn't kill half the population of the city, and they introduced it into the subway system. So looking at subway systems as a potential way of spreading death and destruction is not a new thing that happened in the past 10 years. This is something that people have been worrying about for decades. And we know that the cult in Japan did it very effectively with sarin urate gas. All right. There are different ways that you can regulate the activity of the enzymes. You can have inhibitors and activators, and I forgot to mention the activators here. So some enzymes are produced in the active form, and then you may have an allosteric inhibitor. Some enzymes are produced in the inactive form, and then you may have what we call an allosteric activator. And sometimes you have to have either the inhibitor or the activator to have the non-functional versus functional form. But that's not always the case. So you don't always need to have an activator to replace the inhibitor. So sometimes just remove the inhibitor, and that's good enough. The other way that you can regulate enzyme activity is through gene expression, and we're going to do more with that when we look at cell-cell signaling on Wednesday. So for now, just know that you could regulate how many copies of an enzyme you produce through transcription and translation, but we're not going to talk about that today. I do want to talk about this type of inhibition, which is called feedback inhibition. Then you have a multi-step pathway, and each of the steps is carried out by a different enzyme. And you're making a final product that you need. So in this case, we're using threonine to make isoleucine. These are both amino acids. So you have to have enough isoleucine present, but you don't want to have too much, because if you're making too much isoleucine, it's a waste of your energy to spend that energy to use up all of your threonine to make isoleucine. So you have to balance how much threonine you have versus how much isoleucine you make. Since this is a multi-step pathway, you could regulate the synthesis at any of the steps. Typically, in a multi-step pathway, there is one step that's called the commitment step. So after that step, the rest of the reactions will go forward. So, Gesundheit, if you make the alpha-ketobutyrate, this is alpha-ketobutyrate. If you make the alpha-ketobutyrate, then the rest of the reactions will happen. So if you already made this, then you will make isoleucine. So if you want to stop making any more isoleucine, you have to inhibit the step that leads to alpha-ketobutyrate, not after it, because afterwards these will go forward. This is your commitment step. This is where you regulate. Do you make isoleucine or you don't? And in many of these multi-step pathways, the final product is the inhibitor of the pathway itself. So isoleucine can act as an allosteric inhibitor for the first enzyme. So when you make plenty of isoleucine, then it will inhibit its own synthesis. That's why it's called feedback inhibition. So the product is feeding back into the pathway to stop its own synthesis. As the concentration of isoleucine drops because you're using it, then you remove the inhibition on the first enzyme. And the pathway will go forward and you will make more isoleucine. So the concentration goes up, you inhibit. The concentration goes down, you synthesize. Goes up, you inhibit. Goes down, you synthesize. So you maintain concentrations around the level that you need by going a little over, a little under, a little over, a little under. So far, so good. All right, so let's go back to our curve. And talk about what happens when you have a competitive inhibitor versus non-competitive. Non-competitive might be a little easier, because if the non-competitive is changing the shape of the active site, it doesn't matter how much substrate you provide. So you need a little bit of substrate to get any reaction, and then depending on the concentration of the inhibitor that you have, then you're inhibiting the enzyme. So it doesn't really matter how much substrate you have if you have enough inhibitor to change the shape of all of the enzymes. So above a certain level, you don't get any additional reaction. All the enzymes are blocked. So you get some minimum rate of reaction, and you never go above that. Adding more substrate doesn't make any difference. The enzymes have changed it. And depending on how much inhibitor you have, this could be a little higher, it could be a little lower, but it will be flat. Whether it's higher or lower, doesn't matter, it's going to be a flat line. What happens when you have a competitive inhibitor, where the concentration of substrate does matter? Because more substrate means more substrate can get into the active site compared to the inhibitor. Yes, sir. It will take more substrate to get to the Vmax, so your curve will look like that. So that at any given concentration of substrate with the competitive inhibitor, some of the active sites are still binding to the inhibitor. You have to have a lot of substrate to saturate the enzymes. This begins to saturate here, but when you add the inhibitor, it begins to saturate there. So it requires a lot more substrate to saturate. But you eventually get the same saturation. Because you eventually will overrun all of the active sites with substrate as you increase the substrate concentration enough. With the non-competitive, doesn't matter. You will not overwhelm the enzymes because they have changed shape. With the competitive, you eventually can provide enough substrate that you saturate all of the enzymes and give very little chance for the inhibitor to get in because there's so much more substrate around. It just takes more than when there is no inhibitor around. That make sense to everyone? And I'm going to let you think about that for a little while and see if you have any questions, but we are going to now go to the articles you're reading. So